Namaskar. Today we will start the lecture of, today I will deliver the lecture of linear algebra. So firstly for that we define vector space. A non-empty set, we can say a set V with a field F it's a with field me, it's basically it's over a field F. With two operations. That is scalar, that is addition, which is vector addition, and scalar multiplication. Is a vector space field F if it satisfies the following properties. Following properties. First is A and B are closed under addition whenever A and B are in B. Is basically is vector addition, closed under vector addition. That means vector addition is closed. Or V satisfies the property of, V satisfies the closure property of vector addition. Closure property of vector addition. Now the second is it must be commutative under vector addition. Second is that is A plus B equal to B plus A whenever A and B are in B. That means B satisfies the commutative property of vector addition. Vector addition. That means third is V satisfies the associative property of vector addition. Whenever A, B, C are in B, right? So it is V satisfies the associative property of vector addition. 0 is a vector, that we know well, that 0 is a vector. So with respect to this 0, means it must be true for all v. So that means the existence of identity, additive identity. 0 is a vector. That means 0 is the 0 vector is the identity of vector addition. Next is for each vector v, in v, there exists a negative vector, this vector in the negative direction, v such that means each vector of v has additive inverse in v. Now it is closed under scalar multiplication. That means alpha v belongs to v for all alpha belonging to F, means field, and for all v belonging to v, that is vector. The elements of v basically are the set of vectors we can see instead of set v, that is set of vectors. So the set of vectors v over the field F is said to be vector space if it satisfies the following properties. That is, if it satisfies all these properties. That is, V is closed under scalar multiplication. So this is basically the set of vectors V over the field F. Is a set of vectors V over a field F with two operation is a vector space if it satisfies the following properties. The associative is vectors must be compatible with the scalar associative. That is alpha beta v equal to alpha beta v for all alpha beta belonging to F, means field element, and V is field. That is, this V is compatible, that means the set of vectors is compatible or is associative, is compatibility, it satisfies the compatibility of associative property. That is, we can see with scalars. V satisfies the associative property with scalars, or the vector satisfies the associative property with scalars. Next is, that is alpha x plus y, or we see alpha b plus u, we can take this alpha x plus alpha y. That means scalar multiplication is distributed over vector addition. And it must be true for all alpha belonging to F and for all x, y belonging to V. That is, the scalar multiplication is distributed. Is distributed over vector addition. Next is this. Next is, that is, 1 belongs to 1 is, that is a multiplicative identity, is an element of, it's a multiplicative identity or identity under addition. F such that 1 into V equal to V equal to V into 1 for all V belonging to V. Means the vector satisfies this identity element. Means that is, the 1 is the scalar identity, is the identity of V under scalar multiplication. Or there must exist an identity of V under scalar multiplication. Then we say it is a vector space, right? And the one property that we have left, that is basically is related with the elements of, as the vectors are field elements are also closed under addition, scalar addition. So that means this x into alpha plus beta is x alpha plus x beta, or it's better to write, because they are the scalars and we usually write scalars on the right side, so you can write here. And otherwise the left side, it is the properties of left, if it satisfies left distribution, it means it is, since fields are commutative, so it means that it definitely satisfies the this property. If it is left distributive, then it is right distributive. If it is right distributive, then it is left distributive. So we have this alpha plus beta v equal to alpha v plus beta v. That means vectors are distributed over scalar addition. Distributed over scalar addition. So if it satisfies all these 11 properties, then we say it is, that this is a vector space. Okay. So we have all these properties. Let me see if anything is left. So I have written one extra point which should not be here. That is, the 6th number should not be here, and it must be 6. And that means it is 6. This is 6 as the additive inverse, so that means this is not the 6th. This is 6 alpha b, and this is 7, right? And this one is our 8 point. And this is our 9th, and this is our 10th. So we have 10 properties. This is what is in my mind, that is, we have 10 properties. But if I have written 11, that means what is new property, the new property what I have added. Let me see that. Now we are coming to the examples of vector space. Examples of vector space, right? We have, let F be a field. The n tuples of F is a vector space over F. So n tuples is, let x and y belongs to F of n tuples of F, then x is written as x1, x2, xn, and the y is written as y1, y2, yn. Field is closed under addition. Field is closed under addition. Therefore, xi plus yi belongs to F for all I, where the I is lying between 1 to n. And this means that this x plus y, which is x1, x2, xn, plus y1, y2, yn. Since it is coordinate-wise addition, so we can write this as x1 plus y1, x2 plus y2, and this is xn plus y. And this property implies that all are in F, so it belongs to F of power n. And x and y belonging to this n tuple of F are arbitrary. So this implies that this F, n tuple of F is closed under addition. Closed under addition. Let close under addition. Since field is commutative under addition, commutative under addition. Therefore, this xi plus yi equal to yi plus xi for all xi, yi belonging to F, and it is true for all I where I is lying between 1 to n. So this gives us that this x plus y, which is this x1 plus y1, xn plus yn, is equal to y1 plus x1. It is yn plus xn, which is further written as y1, yn plus x1, xn. And this is equal to y plus x. And x plus y belonging to F, n tuple of F, are arbitrary. That means this n tuple of F is commutative under addition. Associative property. Let x, y, and z belongs to F, tuple of F. That means x is written as x1, x2, xn, y is the same way as y1, y2, yn, and the z is z1, z2, zn. Then x plus y plus z, according to the addition that we have added earlier, is written as x1, x2, xn plus this y1, y2, yn, then z1, z2, zn. And this is further written as x1, x2, xn plus y1 plus z1. It is yn plus zn, which is written as x1 plus y1 plus z1. It is xn plus yn plus zn. Now, field is associative under addition. Field is associative under addition. Field is associative under addition. Therefore, xi, this is plus. Let me write properly. Xi plus yi plus zi equal to xi plus yi plus zi for all xi, yi, zi belonging to f and for all I. So this gives us that this x plus y plus z is now xi plus yi plus zi. Oh, sorry, it's not I, it's a 1 because we are adding the first element. So we write 1. So this is, we are working on this. So this is x1 plus y1 plus z1. And the last element is xn plus yn plus zn, which is written as x1 plus y1, xn plus yn, and this is z1 and zn, which is further written as x1, x2, xn, y1, y2, yn, and this is rz, very much z. So this is x plus y plus z. And this x, y, z belonging to f are arbitrary. So this implies that this, n tuple of f. So this implies that this n tuple of f is associative under addition. 0 belongs to f. That means 0 belongs to f. That means this 0, 0, 0, 0, 0 belongs to n tuple of f, right? Such that x plus 0 is x1, x2, xn plus 0, 0, 0, 0, and this is x1 plus 0, xn plus 0, and which is x1, x2, xn, and which is nothing but x, which is nothing but x. X, and this x, and it is true for all x belonging to a n tuple of f. That means 0 is the additive identity of let x belongs to n tuple of f. That means the x is x1, x2, xn. Now for each xi belonging to f, I is lying between 1 to n, there exists minus xi in F such that xi plus minus xi is 0 is minus xi plus xi or all I. And this implies that this x1, x2, xn is minus x1 minus xn equal to, basically minus I can write here, so I can remove the minus inside. So that is I can, so let me write this is this, and this is equal to x1, x2, xn plus, that is minus 1. I can write this x1, x2, xn, which is x minus x is 0, or I can write x plus minus x 0. Similarly, minus x plus x is 0. That is, for each x belonging to this n tuple of f, there exists minus x in n tuple of f such that x minus x is 0 is minus x plus x. So that means each element of this n tuple of f has an inverse in n tuple of f. Additive inverse. Now we are coming to the scalar part. Let alpha belongs to f and x belongs to n tuple of f. Then alpha into x is alpha into x1, x2, xn. Xi, where there's a f, that means xi belongs to f for all I, means I is lying between 1 to n. Xi belongs to f is a field element, alpha belongs to f is a field element, and field is closed under multiplication. So therefore alpha xi belongs to f, and this means that alpha x for all I, this means that the alpha x, which is alpha x1, alpha x2, alpha xn belongs to f. Well, this belongs to f, so that means each element is in f, so it belongs to n tuple of f. And this alpha and x are arbitrary, one is in field, are arbitrary, so this is n tuple of f is closed under multiplication. Closed under scalar multiplication. So we have to prove all the properties. We can't neglect the properties. Right. Now the next one. Let alpha, beta belongs to f and x belongs to n tuple of f. Then alpha plus beta is definitely in f because field is closed under addition. Addition. So alpha plus beta x is alpha plus beta x1, x2, xn, which is written as alpha plus beta x1, alpha plus beta xn. Alpha, beta are in f, and xi is also in f for all I, and the field satisfies the distributive property of the property of multiplication over addition. Multiplication over addition. And therefore, this alpha plus beta xi is equal to alpha xi plus beta xi for all I. And that means this alpha plus beta x is written as alpha x1 plus beta x1, and this is alpha xn plus beta xn, which is further written as alpha xn, alpha xn, beta x1, and beta xn. We can take out this alpha. This is alpha x1 xn plus beta x1 xn, and which is alpha x plus beta x. Now we are moving to the next property, that is alpha beta x. That this alpha, first let me complete this. This alpha and beta belongs to f, and x belongs to n tuple of f are arbitrary. That means this fn, that means the this vectors or fn is scalarly distributed over vector addition. This fn is scalarly distributed over scalar addition. So is distributed. It's not the scalar because these are the vectors. So that means it's just the vector. It's these are the vectors. So fn is distributed over these vectors. Means now it has become a vector. So fn is distributed over scalar addition. Scalar addition. Now we are moving to the next property. That alpha, beta again belongs to f, and x belongs to n tuple of f. So then alpha beta x is written as alpha beta x1, x2, xn, which is again alpha beta x1, alpha beta x2, alpha beta xn. Means this is this. All are the field elements, and field is associative under multiplication. Alpha, beta, xi belongs to f for all I, and the f is associative under multiplication, associative under scalar multiplication, we can say. Therefore, alpha, beta, xi is alpha, beta, xi. That's true for all I, where I is lying between 1 to n. So that means this alpha, beta, x is alpha, beta, x1, alpha, beta, xn, and which is written as alpha, beta, x1, beta, xn, and which is further written as alpha, beta, and then we can write x1, x2, xn, which is further written as alpha, beta, x. So that means fn is associated with scalars. This is n tuple of f. Fn is associative. Here the field elements F is associative. Now the n tuples of F is associative. Is associative. Over is associative with scalars. Is associative with scalars. Let X and Y belongs to the n tuple of F and alpha belongs to F. It means that this X is again X1, X2, Xn, and Y is Y1, Y2, Yn. Means Xi, Yi belongs to F and alpha 2 belongs to F. And this field is Fs. F satisfies the distributive property of multiplication over addition. So this means that this alpha xi plus yi is alpha xi plus alpha yi for all I, where the I is lying between 1 to n. So this means that this alpha x plus y, which is alpha x1 plus y1, x2 plus y2, xn plus yn, which is now written as alpha x1 plus y1, alpha xn plus yn. Now, since according to this property, this is written as alpha x1, alpha y1, and then we can write alpha xn plus alpha yn, which is written as alpha x1, alpha xn plus alpha y1 plus alpha yn. And this is written as alpha x1, x2, xn, alpha y1, y2. So sorry, it's not the addition here, it's a comma here. Please remember, don't do this mistake. If I did that, please, you will not write this, right? And this is yn. And this is alpha x plus alpha y. That means Fn satisfies the distributive property of scalar multiplication over vector addition. Property of scalar multiplication over vector addition. One belongs to F and xn belongs to, not the xn, it's x only. X belongs to Fn, n tuple of F. But x belongs to n tuple of F. Then 1 into x is 1 into x1, x2, xn. 1 is the identity of multiplicative identity of F. 1 belongs to F. Xi belongs to F for all I, such that 1 into xi is xi for all xi belonging to F, and definitely it is similarly xi into 1 is xi for all xi belonging to F for all I, for all I. And definitely this I is lying between 1 to n. That means 1 into x, which is 1 into x1, x2, xn, is now 1 into x1, 1 into x2 is 1 into xn. And this is x1, x2, xn. Right? And so this is what? This is x only. Similarly, x into 1 is also left distributive. It's if it is satisfying the left properties, then it is automatically satisfies the right properties too. And it is for all x belonging to F and tuple of F. That means F now satisfies all the 10 properties. So this n tuple of F is a vector space over F. Similarly, we can prove, that's an open question for all of you, that similarly we can prove that R of power n, similar questions, similarly, R of power n is a vector space, short form of writing vector space over R. Okay. Rationals Q of n is a vector space over Q. Complex over n is a vector space over complex. Similarly, this complex is a vector space over R2. You will see over R, yes, over reals too, right? So that means that in the similar pattern, you can do all these questions. Now we are moving to the next example. So firstly, let me stop here. Okay, so this we'll start this